Okay, so our next speaker is Patrick Ingram, speaking about abelian arboreal extensions and positive characteristic.
All right, thank you, Jason. I'd like to thank the organizers for the invitation, and thank everyone for coming. The after lunch slot, someone referred to it earlier as the slot of death or something like that. So anyway, if you fall asleep, well, I won't allow it. I'll find a way. So I want to talk about this. This talk is a little gets a little speculative at some time, and parts of it are joint work with Andrea Farragutti and Carlo Pagano, and there's some parts near the end that get even more speculative that I should not implicate them in necessarily, because sort of just speculation. So I'm going to give a little bit of background because I know it's an audience with different backgrounds. So the setup for now is just going to be, we have some arbitrary field and we're iterating some rational function over that field. And we're always working relative to some base point over that field. And we're also going to typically try to sort of think of things up to conjugacy. And here I'm being a little more specific because it'll matter later. Conjugacy over some extension of K, but if I don't specify, then it's going to be over K bar, say. And so, yeah, basically statements we hope are conjugate invariant. And the particular thing I want to sort of think about is the field, the extension generated by the iterated pre-images of some base point. So these are sometimes referred to as arboreal extensions because of the tree that's happening in this picture. If you read a lot of papers in the literature, sometimes the tree's upside down and I think kind of misses the tree image. But here we have A as our base point, and I guess in my picture this is generically, this is a cubic rational function, I guess the way I've drawn it. But the pre-images, and so on generate some field extension. So K infinity F comma A is the extension generated by all of these things. And this tree structure with these edges, if you think about the Galois group, so let's just make some sort of separability assumption here, since I haven't specified the field yet. Let's assume, just so that I can talk about the Galois group, that this all lives in K sep. Then the edge relation in this tree is F. And if F is defined over K, the edge relation has to be preserved, right, by the Galois group. And so this gives you a homomorphism from the absolute Galois group of K into the automorphism group of this tree. And it would not, you would not lose anything in this talk if you assume this tree is always a regular debranching tree where D is the degree of F. So if there's a critical point somewhere in here, it's not going to be a debranching tree. And so the automorphism group is going to be a little bit different because of that critical point. And I would like to avoid thinking about that as much as possible. So let's just imagine this is always a regular debranching tree. So this map here, this homomorphism, is referred to as an arboreal Galois representation. It's not a representation. There are no vector spaces anywhere, but by analogy with the theory of elliptic curves, this is where the representation word comes from. And just to sort of build a little intuition, I'll recall the elliptic, the sort of basics of the elliptic case, so that you can sort of think about what the right conjecture should be or what the motivating statements are. So let E be an elliptic curve over K, over a number field K. Then the over K bar, the L torsion is just like a two-dimensional vector space over FL. So yeah, there's two independent L torsion points for every prime L. And so I guess here, because I started with a number field, I can talk with the algebraic closure. So the absolute Galois group acts on this, and it acts, every element of the Galois group acts like some element of GL2FL once you've chosen a basis. And more generally, if you take the full torsion subgroup, this is like two copies of Z hat, which is the profinite completion of Z. And this gives you, in this case, an actual representation. I'm going to try to use the pointer without moving my slide forward. An actual representation of the absolute Galois group. And the sort of classical result here is if E does not have complex multiplication, in other words, if its endomorphisms are only the endomorphisms that it has to have as a Z module, then the image of rho has finite index in the codomain here. And one corollary of this is that the set of torsion points over K is always finite, but this is kind of a big tool to use. I mean, you can give a pretty elementary proof that the set of torsion points over K is going to be finite if K is a number field, but this in particular implies this. And actually, it's a little bit of foreshadowing. There's a stronger result due to Zarhin. In fact, Zarhin's result is for abelian varieties, but I'm just stating it here for elliptic curves. That in fact, even if you go to the maximal abelian extension of K, you have finiteness of the set of torsion points. And that is a much harder thing to prove. In fact, I don't really, not familiar with the details of the proof of this, whereas the proof of this corollary here is pretty straightforward. So that's sort of the elliptic setting to sort of lay the background down. So a kind of natural question is, how large is the image of rho in the automorphism group of T? So how close is this map to being surjective? Or another way of thinking about it is, to what extent are the relations imposed by F the only, sorry, the restrictions imposed by F the only restrictions on how the Galois group acts on this tree? Actually, I want to point out one more thing about this statement here. If the elliptic curve does have complex multiplication, then those extra endomorphisms give you extra restrictions on how the Galois group can act, and that's why you do not get finite index. But this is a bit of a red herring, because if you take those extra restrictions into account, then you can recover the finite index thing, right? So it's not like there's a fundamental thing. It's just if you have extra endomorphisms, you have extra restrictions you have to obey, and then once you take that into account, the corresponding statement is still true. So I'm going to just give a little bit of background here. These are results that have been around for various amounts of time, and just to sort of bring everyone to the same point in the background. So here's a theorem that is, I guess maybe Nicole's not here yet, but a combination of a bunch of different results, which I'll sort of state as one result, namely for every number field K and every D, there at least exists a monic polynomial of degree D in some base point such that this map is surjective. So I think the original result of O'Doney was that this is true for the generic polynomial, right? So if you have generic coefficients, this is true. And then all these other results are all much more recent, and they sort of prove that there exists an example. The last result is of every degree over every number field, there exists an example which has the generic behavior. So it's at least conceivable that the image here is surjective. One thing I'll mention is that in O'Doney's paper, the conjecture, I think, is this. The conjecture is not just for number fields. So you might, if you're as on the first slide, sort of agnostic as to the field, and if you're not a number theorist, maybe number fields are not particularly special to you, you might sort of ask for the same question about bigger classes of fields. And there's a recent result. So O'Doney conjectured that this is actually true over every Hilbertian field. And there's a recent result that this is not true. So that the full conjecture of O'Doney is not true. So there exist Hilbertian fields over which there is no such example with a surjective. And in fact, I think maybe no example with finite index. I can't remember the exact conclusion, but over number fields, you always have an example with. So Philip Dittman and Boris Kadetz, I think. Yeah. That's fairly recent. Yeah. You need to make some assumption about the field, right? Because like over the complex numbers, this is never going to be true. So you need some assumption, and what O'Doney thought was the correct assumption was this Hilbert hypothesis that the field is not a thin set over itself, and that's apparently not sufficient. But being a number field is sufficient. So. You might, I don't know, you might be able to do something by specializing to a number field. Maybe some sort of specialization theorem, I think. I suspect that's true. We'll maybe talk about it at the coffee break. The question is whether you could prove this for a finitely generated extension of Q, and my hypothesis is if you specialize the transcendental elements, you can only make the image smaller. And so I think probably this gives this to you for any finitely generated. Yeah, I think for transcendental extensions, it should be easier. Here's another example of a result that's not really related to the rest of the talk, but I just, again, wanted to mention it as like the sort of result that is known. So if you assume the ABC conjecture for integers C such that negative C is neither 2 nor a square, you have sort of the analog of Serre's theorem that the image of rho has finite index in the automorphism group of the tree for the polynomial z squared plus C. And two of the authors are, so one's on Zoom and one's over here. Qua's on Zoom. Hi, Qua. So these are sort of the sorts of results one might expect. But in this talk, I'm going to mostly focus on number fields, and then, in fact, later global function fields is sort of the real focus of the talk. So I want to give an example where a sort of interesting example where something contrary is true. So, for example, if you take, just like in the case of elliptic curves, if you look at a rational function that has extra symmetries or extra automorphisms or extra one-sided symmetries, there are various situations where it's easy to show that the action of Galois is more restricted than a sort of generic tree automorphism. And so, sort of like the complex multiplication case, you can easily cook up examples where the image of the Galois group in the automorphism group of T cannot have finite index because of some additional constraint. But then, of course, the natural thing to do is say, well, let's take into account this additional constraint. And one should expect to prove a finite index theorem. But I want to give a sort of more fundamental obstruction or an example where this finite index statement is not true. And this is a result, I have 2014 question mark here because as far as I know, the history of this result is that Rafe Jones was sort of writing a survey paper about these arboreal representations and was communicating back and forth with Richard Pink, and Richard Pink sort of in the email sketched out this argument. So I don't know if it's actually appears anywhere other than in the survey article. But here's a case where one definitely does not have, and for an interesting reason, one does not have this finite index of the image. And that is namely for the key phenomenon here is post-critically finite. So if K is a number field, if K is a number field or a global function field of characteristic bigger than D, where D is the degree of F, and F is post-critically finite, then, okay, if A is not exceptional for F, which I'll explain in a moment, then the image of this representation does not have finite index in the automorphism group of the tree. So I need to sort of clarify a few different things in this statement. So first of all, A being exceptional for F just means that A has finite backward orbit, right? So it could be the case that the point that you're taking iterated preimages of actually only has finitely many preimages, and then none of these questions are all that interesting. So if you take 0 for the squaring map, this doesn't become an interesting question. But it turns out that this is, I mean, exceptional points for rational functions. There is a very short list of things that can happen, and they can be completely described. Being post-critically finite is a property of the orbits of the critical points. So F is post-critically finite if every critical point is pre-periodic. So just some examples, z squared, one can check easily. The critical points are 0 and infinity, and they're both fixed. Z squared minus 1, the critical points are 0 and infinity, and infinity is fixed, and 0 goes to minus 1 goes to 0. This is, of late, my favorite example that I mentioned for a primitive 18th root of unity. This zeta z squared plus 1 over z squared minus zeta squared. The critical points are 0 and infinity, and one of them is 2 periodic and one of them is 3 periodic. These are examples of post-critically finite rational functions. And I'm going to just sort of quickly sketch the proof of this statement because it it's really just the combination of a few other known results, and I will refer back to generalizations of some of these things, or maybe not generalizations, but related results. So the proof of this is a combination of two things. So the first is a theorem of, in the case of polynomials, Aiken, Hajir, and Mayer, and in the case of rational functions of one variable, Cullinan and Hajir, that if f is PCF, then k infinity, so here I'm choosing some base point and taking this iterated pre-image field, is ramified above only finitely many places. So again, k here should be a number field, sorry, as in the statement of the theorem, or also a global function field. So if f is post-critically finite and you look at one of these iterated pre-image towers, you get ramification above only finitely many places. You would expect maybe some tower of number fields generically to be ramified over infinitely many places. And then the second result is just some algebraic number theory, which says something about extensions that are unramified outside a finite set of places. So this is really a result of Ihara, but this particular formulation of it is in a book of Neukirch, Schmidt, and Bingberg. And it just says that if you have, again, a number field or a global function field under certain additional hypotheses, but let's just say a number field for now, the Galois group is of the maximal extension unramified outside of some finite set of primes, is generated by finitely many conjugacy classes. Something like this is true in global function fields too, but you have to worry about wild ramification. And so that's what the restriction on the characteristic and the degree avoids wild ramification. And so then it's just a matter of sticking these two things together. And the proof really shows that the image of rho has infinite index in the Abelianization of the automorphism group. And in fact, it's a finite subgroup. So within the Abelianization of this automorphism group is just countably many copies of the integers mod 2. And the image of this will be some finitely generated and therefore finite subgroup of that. And so once you pass the Abelianization, it's easy to show that the image of rho has to have infinite index. So this infinite index statement here is not just some extra restriction on how the Galois group acts on this tree. There's really some sort of arithmetic going on underneath. And as I was writing up these slides, it occurred to me that I don't think there's anything here that doesn't work for a post-critically finite endomorphism of a projective variety. And you can make this same argument work. So in particular, so it's number fields and global function fields of characteristic bigger than D. Yeah, so you need tame ramification in this for the function field case, and the characteristic restriction gives you that. Yes, and so in particular, this result here, this Cullinan-Hajir thing, you can extend it, you can sort of massively generalize it. And so this proof should work in all those cases. Okay. So one might in general expect that the image of the Galois group of k infinity over k is large in the automorphism group of T. We've seen some examples where finite index can be proven. But it might be sort of too hard to prove this in general. Certainly there's a lot that's not known. And so one sort of alternative question you might ask is whether you can show that the image of Galois, or the action of Galois on this tree, is sort of not tiny in some sense, some other sense of not being too small. So as one really simple example, it's easy to show that the Galois group of this extension is at least not finite. In other words, k infinity is at least not a finite extension, unless you have this special case where A itself actually only has finitely many pre-images. That's a simple argument involving heights, but it's not. It's like 99% obvious, not 100% obvious. But that's one sense in which this group is not tiny. So another sense in which maybe you might want to know whether or not it's tiny is whether or not it's abelian. Right? So presumably any abelian subgroup of the automorphism group of this tree must be relative to the full group small. Right? So being abelian is maybe a measure of being small. So one might ask, when is this this extension k infinity of fa an abelian extension of k? And maybe I'll mention this conjecture, and then I'll sort of give another version of why you might think this is interesting. So this is a conjecture of Jesse Andrews and Clay Petchy from a few years ago. The conjecture is just for polynomials at this point. So let f be a polynomial and take some non-exceptional starting point A and look at this pre-image extension. Then the conjecture is that this is an abelian extension, basically if and only if it's one of the examples where you know you have to have an abelian extension. So if and only if up to conjugacy, the pair FA is the power map with a root of unity. So that will definitely give you an abelian extension, or something similar, a Chebyshev polynomial and twice the real part of a root of unity, and you can check that those also give you abelian extensions. And the conjugacy, in fact, should be over KAB, so over the maximal abelian extension of K. So certainly, if you are conjugate to one of these things over the maximal abelian extension of K, then this arboreal extension you're building will be an abelian extension of K, but the conjecture is that those are the only cases. I want to give you maybe sort of another reason why you might believe this, other than just the idea that the image of Galois should be not tiny. Another reason is, this is sort of related to Laura's talk, right? If you have, for example, two rational functions with many common pre-periodic points, like let's say infinitely many, you might expect that they have to have some sort of dynamical relation between them, right? And so, and you can make similar statements about pre-images. If you have sort of pairs FA and GB where there are infinitely many common pre-images, there should be some sort of dynamical relation. Here, we're not asking about common pre-images of anything, but you might speculate that, in fact, even if just the fields generated by these pre-images, let's say the pre-images of A under F and the pre-images of B under G, if there's a lot of overlap in those infinite extensions, maybe there should be some dynamical relation that forces that, right? And so you can think of the maximal abelian extension as, well, it's not quite the full thing you don't get that exactly when you pull back a particular root of unity by the power map, but let's say over Q, the maximal abelian extension over Q is the field generated by the pre-periodic points of the squaring map or the Dth power map. And so the conjecture might sort of be that there shouldn't be too much similarity between the field generated by the pre-periodic points of the powering map, which is a sort of dynamical infinite extension, and the pre-images of something under a polynomial, unless that polynomial is closely related to the power map, which is exactly what these two examples are. Okay, so there in fact have been many results since this conjecture. I mean, a lot of progress has been made in this conjecture, and so I'll mention three results. First of all, in the original paper of Andrews and Petchy, they proved a few special cases of this. For example, they proved that the statement is true if F is k-bar conjugate to a powering map or a Chebyshev map. So going back to the conjecture, they're sort of saying, if you have like 1 foot in the door of being one of these two exceptional cases, then you're fully in that case, right? So your conjugacy is actually a KAB conjugacy, and your base point is actually a root of unity or something like this, right? So if you have the right polynomial up to k-bar conjugacy, then you actually have the right polynomial and base point up to KAB conjugacy. Another result in this direction, due to Andrea and Alina Stoffe and Umberto Zanier, is that the conjecture is actually true for Q, if the base field is Q, and it's true if F is not post-critically finite in general. And this is for rational functions, in fact. So the conjecture is true if you are dealing with a non-post-critically finite rational function, which is most rational functions. And finally, so now, of course, you're reduced to the case of these post-critically finite rational functions. And very recently, Clay Petchy and I think Shifan Young proved that for post-critically finite rational functions, the conjecture is also true if A is not a pre-periodic point for F. So for most rational functions, the conjecture is true. And all of this sorry, I should have said all of this is true over number fields. I think I stated the conjecture over number fields. So for this conjecture to fail at this point, you need a you need a PCF rational function and a pre-periodic point, which actually gives you a lot of hope for proving the conjecture, because you now have a lot of structure in the only case where this can fail. Okay. So what I want to talk about is the analogous question over a global function field. So all of that was over a number field, but certainly over other arithmetically interesting fields, you can ask the same sorts of questions and you might hope the same sorts of things are true. So what about a global function field? So for example, if k is fq of x, where x is a curve over fq, well, you can cook up the same setting. You can take some point on p1 of k, and you can look at its iterated preimages and join that to k, and you get some, I think of it as a tower. I've written it as a single infinite extension, but it's naturally a sort of tower of fields. You can ask, when is that an abelian extension of k? And one should note that here, there's an immediate problem. There's an obvious thing that can happen. Namely, f and a could happen to be defined over the finite field, the field of constants. And then all of your extensions are finite field extensions. And those are always going to be abelian. And so your preimage field, well, since we're adjoining it to fq of x, it's still a function field over x, but it's contained in fq bar of x, which is an abelian extension of fq of x. So here there's a new sort of pathology, namely things being defined over the constant field. And as in Laura's talk, we'll refer to, I think I already defined isotrivial. So we'll define the pair to be isotrivial if and only if it's k bar conjugate to a pair defined over fq bar. And you can sort of check the details. Of course, if you have an isotrivial pair, there might be some sort of non-constant field extension happening at the beginning. But you'll have, after some finite extension of the function field, you'll have only a constant field extension in this infinite extension k infinity f alpha. And so k infinity will at least be virtual abelian over k whenever you have an isotrivial pair. Okay, so that has to be an exception in our statement. And what we managed to show with a few hypotheses is that at least for some class of rational functions, so we started off with polynomials, but the proof is a little bit more general than that. Then in fact, so the setup here is we have a rational function over a global function field. And I want to make this additional hypothesis that we've already seen in a different result, that the characteristic is at least d, strictly bigger than d, to avoid wild phenomena. Then at least if the rational function has a super attracting cycle, this infinite extension is going to be abelian if and only if you have, well, first of all, f comma a is an isotrivial pair, and second of all, that you have, in fact, an isotrivialization over the maximal abelian extension of k. So you can do your change of variables over the maximal abelian extension to make your pair defined over the constant field. Having a super attracting cycle means that you have some periodic point where the derivative vanishes, or alternatively, you have a critical point which is periodic. So this is sort of like so for a polynomial, the point in infinity is a fixed critical point. And so this is a sort of generalization of being a polynomial. The other point I want to make is that you still have these exceptional cases from the Andrews-Petschek conjecture, like the powering map and so on, but they are all isotrivial. So those exceptional cases, in the function field case, those exceptional things that can happen are all subsumed by isotriviality. So that.
Was there a conjecture about polynomials, or how did they formulate it? I've already forgotten.
Their conjecture was about polynomials. Yeah.
Oh, I see. But one of the theorems you mentioned was also about rational functions.
Yeah, exactly. Yeah, and for rational functions, you should expect additional exceptions. I think
Lattice examples.
Yeah, lattice examples from, so the so-called rigid lattice examples, the lattice examples from elliptic curves with complex multiplication, I think should give you exceptions to that. I don't know if you'll get abelian extensions or, virtual abelian. They might be virtually abelian, yeah. So there might need to be a finite extension until, after which they become abelian. So what I'm going to do is I'm going to sort of walk through the proof of this theorem. And then I'm going to devolve into sort of wild speculation about other cases. So, but first I want to just sort of go through roughly how this proof works. So the first step is an argument that's in already this paper of Faragoudio, Safe, and Zanier in the number field case. So in fact, a large part of this paper is statements in number fields that we wish were true in function fields, and then it turns out they are true in function fields, but sometimes slightly different techniques are needed. So here's a sort of key lemma. If k infinity, so this is again, given that p is bigger than d, which will be an hypothesis that comes up again and again, if this arboreal extension here is abelian, then the extension is ramified over at most finitely many places. And the proof of this, so here I'm going to do some hand waving because there are concerns about certain polynomials being identically zero and so on. Basically, the characteristic assumption here allows you to not worry about certain derivatives being identically zero. So, okay, if we write our rational function as f1 over f0, after sort of throwing away finitely many bad primes, I'm claiming this extension is ramified over only finitely many places, so I'm sort of free to add extra finitely many primes to my set S that I'll ignore. Every extension of the form k adjoin f inverse beta over k adjoin beta is going to ramify at most above primes dividing this discriminant, and this discriminant is some polynomial in beta. And now using the fact that this extension here is Galois, if you get ramification at one prime above a prime at the base, you actually get ramification at all the primes. And you can use that to give a lower bound. So if you have some prime that ramifies, you can use that to get a lower bound on the height of this discriminant. And this discriminant here, as I mentioned, is a polynomial in beta. You can just, I mean, for f fixed and beta, so you're taking pre-images of different things, but f is fixed. So for f fixed and beta varying, this is just some polynomial in beta. On the other hand, you're taking iterated pre-images of some point, and it's a basic fact about heights that is going to be an infinite set of bounded height. And so this, if you're looking at iterated pre-images of a particular point, this quantity is bounded independent of the thing you're taking, sorry, independent of which pre-image you're looking at. So this height of delta of beta is going to be bounded above in terms of the height of beta, and that's going to be bounded above in terms of f and the thing you're taking inverse images of. And so that gives you some upper bound on primes that ramify in this extension, and so they're only in, I guess, in the case of a function field or a number field, it's upper bound on the norm of the prime. And so that gives you only finitely many primes that ramify in one of these extensions if the extension is abelian. And I was mentioning, I think, to Tom, I haven't really thought about this too much, but this proof, in fact, no part of the proof of this theorem actually uses the fact that this extension is abelian, except that we use the fact that every intermediate extension is Galois over the base thing. And so in other words, we use the fact that the Galois group has the property that every subgroup is normal. And abelian groups have that property, but there are non-abelian groups that have that property. I strongly suspect the non-abelian groups that have that property cannot show up as these Galois groups because they're very restricted in what they can be. But strictly speaking, what we're using here is not the fact that this extension is abelian. We're using the fact that every intermediate field is Galois over the base. Okay, step 2 of this proof. So the second step requires, again, a function field version of a statement that was made initially over a number field. So I should say, in this theorem as dated, this is for number fields. And what we need to do is make a function field version of this. So the statement from this, this is from an AIM workshop, which is why there are so many co-authors. So me and this gaggle of other people prove this theorem. In our defense, I do want to say that Rubinstein-Salcedo is a hyphenated name, so it's not. And I think, so I sometimes claim that there are more authors than pages in this paper, but I think that's not actually true. I think that the paper is longer than whatever that is, seven pages, but not much. So this is an AIM workshop result. But the result is that this extension, this K infinity FA, ramifies over at most finitely limiting places in the number field setting, if and only if F is PCF. And I've added or isotrivial because part of the proof here was checking that this is true for function fields. Again, I haven't written on this slide, but always, oh no, I have written it on this slide, always under this characteristic assumption. So one direction of this is this result that I put up of Cullinan and Hajir that gives, well, I'm not going to decide whether it's the if or the only if statement on stage, but the converse was sort of the value added here, that if you have any extension like this for a non-exceptional that ramifies over only finitely many places, then in fact your rational function is postcritically finite. The sort of, I don't want to say easy direction, but the previously known direction generalizes to PCF endomorphisms of any projective variety off of a proper Zariski closed subset of starting points. But this direction, we only know how to do for rational functions of one variable. And so this is, we sort of extended this to function fields of positive characteristic, and there's a little bit of stuff that's needed. So the original result, for example, uses a bunch of different things, but it uses results like Falting's theorem. And this is where non-isotriviality comes into the picture here, is in those applications of results from arithmetic geometry like Falting's theorem. We need the corresponding non-isotriviality statement for points on curves. So, sorry, the conclusion here is that in our setting, K F A over K abelian now implies that F is PCF. Or isotrivial. If it's isotrivial, then we can skip to the next step. So step 3 is, okay, what do the PCF maps look like? And again, in the complex setting, or I don't know if I should say again, because I was talking about number fields before, but in the complex setting, this is something that's known. So I've stated it maybe here in a slightly unorthodox way, but it is a consequence of a result of Thurston, that any PCF map in C of X, so here X is supposed to be a curve over the complex numbers, is isotrivial or one of these families of lattice examples. I haven't defined them, but thankfully Laura told us all the Samuel lattice. And so again, one might ask about what is the corresponding statement in the function field setting. And this is actually a situation where it's a little bit embarrassing, but Carlo and Andrea at some point got in touch with me and said, do you think for rational functions with a super attracting cycle, we could prove the same thing in positive characteristic? And I said, yeah, this is the sort of thing I've thought about. I'm sure I can come up with some sort of argument. And I spent half a day sort of sketching out the argument. And then I looked something up in a paper of mine, and I realized that the statement was in the paper already. So neither of us had read that paper, apparently, or none of us. I guess there were 3 of us. So again, given that P is bigger than D, if F is PCF and has a periodic critical point, then F is isotrivial. So at this point, if you have an abelian extension of this form, it at least implies that F is isotrivial. So at this point, we've lost track of A, right? We just have the isotriviality of F. So without loss of generality, we can assume at this point that F is defined over FQ bar, but A still might be non-constant. And for this last step, so how do we show that A would also have to be constant? I guess there's a mini step 5. This goes even farther back. So this is, we need an idea that is due to Butcher in 1904. So in complex dynamics, there's this result. Let's just, maybe I'll say the version that's for polynomials. There's a sort of old idea of Butcher that if you have a polynomial of degree D near the point at infinity, it just looks like the Dth power map in some sense. So you can express this in terms of there being some biholomorphism or something. But if you just iterate a polynomial of degree D and you're close enough to the point at infinity, it just looks like Z to the D. right? Just intuitively, all the other terms are just too small to do anything. And so we needed a version of this for rational functions with a super attracting fixed point. So here, the point at infinity for the polynomial, you can replace with any ramified fixed point. And it turns out that there's a similar statement in non-Archimedean fields. If you have, over a non-Archimedean field, if you have a fixed point that is ramified, then locally you can conjugate your map to the power map. And that conjugation is actually going to be Galois equivariant. So it can give us information about Galois. This result was sort of motivated by Tate's non-Archimedean uniformization of elliptic curves, which gives you one way of approaching the image of Galois, is to sort of localize at some non-Archimedean place where you have a nice uniformization, and that uniformization is Galois equivariant. Basically, that just means your power series here has coefficients in the ground field. Yes, I think I've done one of my compositions on the wrong side. Yeah. So it should be pre-composition on one side and post-composition on the other side, not pre-composition on both sides. Yes, thank you. That should be omega composed with F. Yeah. Okay, so what does that mean? Well, if A is non-constant, if F is defined over your constant field, but A is non-constant, then it has a 0 somewhere. That 0 is an absolute value on the function field. I mean, that place where A has a 0 is an absolute value on the function field in which A is inside, strictly inside the unit disk. And this local conjugacy, once you move up, once you tensor up to the completion at V, gives you a Galois map, a Galois equivariant map to the pre-image tree of some non-root of unity under the ETH power map. And that contains non-Abelian stuff. And so basically in your field here, once you extend scalars to the completion, your infinite tower of function fields has already some non-Abelian stuff. And so it must have had non-Abelian stuff before you localized here. One thing I want to mention is sometimes people, especially with respect to Tate uniformization, they say that, if you do this over the real numbers, you don't get a Galois equivariant map. But that's not true. It's more, so Butcher's result and the Tate result does give you Galois equivariance. It's just that the Galois group of like R over C is not that interesting, right? So it just says that your thing commutes with complex conjugation. So here you get a bigger, more interesting Galois group. So the last part of this argument, so we've shown that any pair with a superattracting fixed point such that this extension is abelian is K bar conjugate to a pair defined over the constant field, or the algebraic closure of the constant field. And the last step is just to check that this K bar conjugacy is actually a KAB conjugacy. And this turns out to be way simpler than I suspected it might be. The point is basically you have this conjugacy between two maps, and it moves the infinitely many preimages of your point to the infinitely many preimages of your point, and all of those things are in KAB. So once you have a Mobius transformation moving 3 points to 3 points, you can solve for the coefficients, right? And so the fact that you have these infinite sets in KAB that are being moved one to the other by a fractional linear transform just automatically gives you that the fractional linear transform is defined over that field. And then I claim the other direction is easy. So the other direction is if you are isotrivial over KAB, then that extension really is abelian. Okay. So every step, so I have a summary of my argument. Every step used the fact that P was bigger than D, right? So in fact, I think this is true. It's always hard to say whether or not an argument really has to use this, but it seems true that every single step uses the fact that P is bigger than D. And when I first started thinking about PCF maps and so on, I was always thinking about, or talking about polynomials of a certain degree, and you're reducing mod various primes. So you're moving this direction. And so this is a very happy picture eventually. But here, if you're thinking about function fields, you're fixing a prime, and then you're thinking about rational functions of various degrees. And so there's, instead of there being only finitely many primes that are a problem, there are only finitely many degrees that are not a problem. And so this becomes a sort of unfortunate picture when you look at the other side. This is generated by Google Gemini, and I gave up on, it was supposed to give me a picture at some point with a thumbs up and a thumbs down, and AI is not that advanced yet. And so I gave up on that. So in the last 5 minutes, I want to ask the slightly frightening question about what about when p is less than or equal to d? So what happens when the prime is smaller than the degree? And the first thing I want to point out is that there's certainly new examples of these arboreal extensions which are abelian. And so here's a concrete example over fq adjoined t. This polynomial, tz plus z to the q, for any preperiodic point, this arboreal extension will turn out to be abelian. And that is, now that I'm saying that, I'm worried they might need to make a finite extension and then it's abelian. It's at least virtually abelian, but I'm pretty sure it's in fact abelian. If you're familiar with Drinfeld modules, you may recognize this as the sort of defining polynomial of the Karlitz module. And this is a non-isotrivial example. And so how do you know it's non-isotrivial? If you sort of think dynamically, the fixed point at 0 here, the multiplier is t, and that's a conjugacy invariant. And so no matter how you change coordinates, the fixed point, whatever fixed point 0 gets moved to, will always have multiplier t, which is non-constant. So this has to be non-isotrivial. So in general, if you take any, I'm trying to summarize this a little more quickly. If you take any affine curve with one point at infinity and let A be the function field of that affine curve, a Drinfeld module is a homomorphism from A to the endomorphism group of the additive group. In general, and there's some quantity associated to it called the rank of the Drinfeld module. Maybe I won't get into a proper definition. This definition of R at least makes sense if this is the affine line. And in general, the endomorphism ring of a Drinfeld module is some A module of rank at most R. This is in the case of generic characteristic. In general, it's R squared, but I'm going to assume generic characteristic here for people familiar with Drinfeld modules. And phi has complex multiplication if and only if the endomorphism ring has the maximal possible rank. So for example, over fq of t, this Karlitz module has rank 1, and so its ring of endomorphisms is at least A, so it has rank 1 over itself, and so that's a CM example. More generally, I find that nobody writes down examples of Drinfeld modules with complex multiplication, at least not in the places I've been reading with Drinfeld modules. If you take any polynomial p, that same phi defines a Drinfeld module of rank degree of p over the subring fq square brackets p, and that will always have complex multiplication. If you want to write down examples of Drinfeld modules with complex multiplication, this is in general what they look like. And here's a quick proposition you can prove. This is not sort of a statement, a deep statement, but this is just gluing together a few known results about Drinfeld modules. If you think about these arboreal extensions for endomorphisms of Drinfeld modules, then it turns out you get an abelian extension if and only if phi has complex multiplication and B is a torsion point. And so a question, I don't know if we want to make it a conjecture, but a question we have is whether, at least for separable polynomials, I want to talk about separable polynomials because I want to do Galois theory. The question is, are the only examples of abelian extensions of this form coming from isotrivial pairs, and then things that are sort of semi-conjugate to endomorphisms of Drinfeld modules? Or if you prefer, just additive polynomials at the top, but I want separable additive polynomials so they can always be strong-armed into a Drinfeld module. But it's the theory of Drinfeld modules and complex multiplication that gives you the finiteness sometimes. And so that's sort of the question. So that's maybe our weak conjecture that in the small characteristic large degree case, there are additional examples, but maybe they only come from these things that I'm sort of tentatively calling Drinfeld-Lattez examples because they have the same picture as the Lattez maps, but they come from GA instead of elliptic curves. The other question I want to quickly look at is the question of the PCF locus in small characteristic, because the argument that we made really comes down in several key places to understanding post-critically finite rational functions. And you can certainly still define post-critically finite polynomials and rational functions in whatever characteristic. I'm going to ignore separable, sort of inseparable polynomials. I claim they're all PCF, but I will just set them aside as pathological examples. But there are certainly non-isotrivial families of PCF polynomials in characteristic smaller than degree, less than or equal to degree. For example, this family I already wrote down. This is a family of PCF polynomials, and it's non-isotrivial. So this result, this sort of Thurston-inspired result, that there should be no algebraic families of these things, for polynomials, none at all, because the Lattez maps are properly rational functions. That's just not true in the case of characteristics smaller than degree. And I want to give a couple other examples. So you might think that previous example is sort of an unfair example because it has no critical points. So it's sort of vacuously post-critically finite. But here's a large class of examples that show that you can write down all sorts of, when the characteristic is smaller than the degree, you can write down all sorts of high-dimensional families of post-critically finite polynomials. So if you take anything with a big inseparable factor, and a fixed point at 0, you quickly send a lot of critical points to 0. And so just this family of examples shows that the locus of post-critically finite polynomials in this low characteristic case should have components with dimension at least d over p, because you can write down something that's mostly inseparable multiplied by a small power of z. Okay, but even the inseparable factor part is not the only thing that's going on. So here's a family, this sort of vaguely accusatory diagram. This is the critical portrait of this 2-parameter family of maps over F7. And this does not have inseparable factors. This is exactly one of these Drinfeld-Lattez families. It's semi-conjugate to the family of rank 2 Drinfeld modules, or a particular endomorphism from the family of rank 2 Drinfeld modules over F7. There's nothing special here about F7. This could be Fp with the 8 of p plus 1 and the 6 of p minus 1. And this is another family of polynomials, non-isotrivial family of polynomials with the same critical portrait. And it's 2-dimensional compared to degree 49, I guess. But this is a little different from the last example because there's no obvious inseparable factor. And in fact, having a big inseparable factor is a conjugacy invariant. So if there's no obvious big inseparable factor, there is no big inseparable factor. Okay, so there's a lot that could go on. And at some point, many years ago when I was thinking about this, I completely gave up because it seems like, well, the analog of Thurston's result is just not true in small characteristic. But it turns out that you can at least say something. So just to sort of set the context, when d is smaller than p, this actually follows from a result that I put on a previous slide, but this is a weaker statement that was known earlier. So if the characteristic is bigger than the degree, then the components of the PCF locus are 0-dimensional. So this is sort of this rigidity statement. You don't have any algebraic families of PCF polynomials of degree d when the characteristic is bigger than d. And so I'm trying to generalize this to degree bigger than p. And what I've been able to do so far is at least handle that next sort of little range of degrees. And so the statement, which probably by now you've read, is that for polynomials of degree greater than or equal to p, but strictly less than 2p, this PCF locus at least has only 1-dimensional components. So there are algebraic families, non-isotrivial algebraic families of PCF examples. I've shown you some. But you can show that there are none of dimension bigger than 1. And in a few cases, I've gone through the argument to show that there are, in fact, infinitely many distinct ones of dimension 1. But at least there are none of dimension bigger than 1. And so, of course, the conjecture should be that this example that I showed, that the PCF locus, the components are no bigger, or sorry, are at least about size d over p, that should also be the biggest they can be. And this is the proof of that for the first range of values bigger than p. So we know when d is 2p, we will have some two-dimensional components. And so I'll let you know how the proof of the rest of that result goes.
Questions?
What's the obstacle for doing that for rational functions? Is it that isospectral?
For which
Oh, the result on this last page.
on the last slide?
Yeah.
Yeah, so the proof, so these papers here dealing with PCF polynomials in particular, very concrete and very hands-on, sort of proving specific things about polynomials and certain normal forms and the coefficients and so on. And this argument is the same sort of thing. And so for the results about PCF maps over number fields or whatever, you need to sort of bring in additional machinery. And I don't know how to do that. Even in that case, the p bigger than d for rational functions in general, I don't think that's known, that there are no that other than lattice maps, there are no non-isotrivial families of PCF maps. So it is known that a family of PCF maps in characteristic p bigger than d will be isospectral. So that all the multipliers will be constant, but the step from that to isotrivial, I don't think is known in positive characteristic. But for this case here, I don't know. I'm afraid to even start thinking about rational functions at this point. Yeah.
But you think maybe having a super attracting?
Maybe it might be
Something
possible.
like
Yeah,
that.
it might be possible to generalize this statement to rational functions with a super attracting fixed point. Like that seems like that's not too big a jump.
Any more questions?
Do you know if the critical locus is pure?
In the case of,
Degree between p and 2p.
yeah,
Okay.
it should be, yeah. Oh, sorry, the critical locus or the PCF locus? Oh, that's a different question. No, I do not know that. So the proof in fact shows that components have dimension either 1 or 0, and then it becomes a question of, are all those points lying on curves that are in here, should they be counted separately? So no, I don't know if there are some there. In fact, I strongly suspect there are countably many sort of, when counted properly, isolated PCF examples. So there should be both rigid and flexible PCF polynomials here, I think, but that's not based on anything other than kind of my own intuition and the way the proof breaks down into two cases. Yeah, so sorry, the PCF locus, the critical locus of a polynomial is going to be pure, but the PCF locus here, I strongly suspect is not pure. I think it's a union of points and curves.
Any other questions? If not, let's thank Patrick again. Now we have a coffee break now until 3:30.